In high-end conflict, the side that sees first wins. Detection is dominance. For over 3 decades, the Northrop Grumman B2 Spirit has owned that advantage. At roughly $2.1 billion per aircraft, it represents one of the most sophisticated engineering achievements in military aviation, a flying wing sculpted to slip through the world's most lethal tracking systems. Its design philosophy is simple but ruthless. Deny the enemy targeting information long enough to strike first. But stealth is not a magic cloak. It is not invisibility in the science fiction sense. It is a stack of carefully calculated engineering trade-offs. Every angle, every material layer, every inlet curve exists to defeat a specific type of radar. And here's where the physics turns. If you step away from modern high-frequency X-band radar and return to the long wavelength radar technology first developed in the 1940s, the rules change. The ghost doesn't vanish. It begins to bloom. Today, we break down what engineers call the resonance problem, the one wavelength trade-off stealth technology can reduce, but never completely eliminate. Chapter 1. The Mirror Trap. Modern stealth is primarily designed to defeat fire control radars. These are the radars that guide missiles. Most of them operate in the X-band, using electromagnetic waves roughly 3 centimeters long. At that scale, aircraft surfaces behave like mirrors. Vertical tail fins, flat fuselage panels, and right angles reflect energy directly back toward the radar source, creating a bright return on the operator's screen. That return is called radar cross-section, and traditional fighters like the F-15 light up dramatically in this band. Stealth aircraft solve this through geometry. The principle is called specular reflection. Instead of allowing radar waves to bounce straight back, surfaces are carefully angled so incoming energy is deflected away into empty sky. Edges are serrated, intakes are curved, exhaust paths are shielded, even access panels are aligned with precise angular discipline. On radar, this reduces the aircraft's apparent size by orders of magnitude. To an X-band system, the B-2 may appear no larger than a small bird. This geometric shield works because X-band wavelengths are tiny compared to the aircraft itself. The radar sees only local surfaces. Each panel behaves independently, like individual mirrors redirecting light. As long as the shaping is precise, the energy goes somewhere harmless. That is the core of modern stealth doctrine, designed for the high-frequency fight, the one that controls missiles. Chapter 2. The Resonance Hub. But physics has scale, and scale changes everything. While stealth aircraft are optimized for centimeter-scale wavelengths, many early warning radars operate at much lower frequencies, in the VHF band, where wavelengths stretch from 1 to several meters. These systems trace their conceptual lineage back to World War II radar networks. The waves are longer, slower, and dramatically larger in physical size. When radar wavelength becomes comparable to the major structural dimensions of an aircraft, wingspan, fuselage length, tail spacing, geometry loses dominance. Instead of interacting with small surface features, the wave interacts with the aircraft as a whole structure. This is where my resonance enters the picture. Imagine ocean waves striking a ship. Small ripples bounce harmlessly off the hull. But when a massive swell matches the length of the vessel, the entire structure begins to move with the water. It is no longer about reflection. It is about coupling. The wave grabs the object. Similarly, when a meter-scale VHF radar wave encounters a stealth wing of comparable scale, the aircraft can no longer simply deflect the energy. The electromagnetic field induces distributed currents across the airframe. The structure begins to re-radiate energy. Instead of acting like angled mirrors, the aircraft behaves like an antenna. This is not because VHF radar is more advanced. In fact, it is technologically simpler. It works because the wavelength is too large to be cleanly redirected by geometric shaping. The stealth jet blooms on the radar screen, not brightly, not precisely, but detectably. The invisibility optimized for centimeters cannot fully suppress physics at the meter scale. Chapter 3. The lethality gap. So if 1940s-style radar can detect a stealth bomber, why invest billions in building one? Because in warfare, detection is not destruction. VHF radar is excellent for early warning. It can tell a commander that something unusual is in the sky. But its long wavelength comes with a cost: poor resolution. The same physics that allows it to detect large-scale resonance also prevents it from producing sharp, precise targeting information. Instead of a crisp lock, it provides a blurry indication, perhaps a 3-mile box of uncertainty. Missiles do not fly toward boxes. They require weapon-quality tracking. That precision comes from high-frequency fire control radars, the same X-band systems stealth aircraft were designed to defeat. To guide a missile accurately, the enemy must transition from VHF detection to X-band targeting. And here the geometry reasserts itself. When the tracking radar switches to high frequency, the stealth shaping once again deflects the energy. The radar cross-section collapses. The target flickers. The lock becomes unstable. The enemy knows something is present, but achieving a stable missile solution becomes exponentially harder. This is the lethality gap. Long-wave radar can see you. Short-wave radar can kill you. Stealth is engineered to survive the second, not necessarily eliminate the first. The Northrop Grumman B2 Spirit is not an invisible ghost. It is a calculated compromise. Its design accepts that long-wavelength systems may detect it at range, but ensures those detections rarely translate into precise, weapon-quality targeting. Stealth is less about total invisibility and more about denying the enemy the ability to finish the kill. Modern engineers understand the resonance trade-off. Today's platforms integrate broadband, radar-absorbent materials, refined shaping across multiple frequency bands, and electronic warfare systems that disrupt tracking solutions. Stealth has evolved beyond simple geometry into full-spectrum management, blending materials, science, signal manipulation, and data fusion to exploit the gap between detection and engagement. The next-generation Northrop Grumman B-21 Raider advances this philosophy further, combining radar reduction with infrared suppression, cyber resilience, and networked survivability. Because the battlefield is no longer single-band, it is layered. Stealth is not dead. Radar is not obsolete. Both are evolving. The advantage goes to the side that adapts faster and understands the physics driving the fight. And the next frontier isn't just about radio waves, it's about heat. Infrared seekers track thermal contrast, not radar cross-section. If you want to see how next-generation bombers suppress their infrared signature and disappear against the sky's background radiation, comment thermal below. Subscribe for the next briefing. Dismissed.